Hi guys, we are on Unit 1, Day 2, and we're going to talk about the next type of vector application. In this lesson, we're going to be looking at velocity as a vector. So a couple quick things, and we did talk about velocity in Unit 1, so this is really a continuation and just sort of a little bit of some more complicated questions, but along the same lines as what you already did with velocity in Unit 1. So velocity is related to speed. We sometimes kind of in regular use them interchangeably, but speed is a scalar quantity, so it has only a magnitude, and velocity is a vector quantity. It will have magnitude and direction. So if you're talking about speed, that's just the magnitude portion of the velocity of an object. Okay. If now velocities as vector addition often come into play if an object's being is moving independently in one direction and being pushed in the same direction or in an opposite direction by another velocity. One of the most common situations with this, so common that I kind of use the general formula as this, use this example as like a general formula for this, is with a plane and wind. So for instance, if a plane is flying and the wind is from behind the plane going in the same direction as the plane, that will push the plane and make it go faster. If the plane is flying, say, north, and the wind is going in the opposite direction, say south, that will slow the plane down and make it travel more slowly. So we can take a look at this. If they're going in kind of the exact same direction or in exact opposite directions, it's much easier. But if they're going kind of at different angles to each other, not like a 0 degree or 180 degree, we have to use vector addition. Now, kind of in general, I like people to kind of think of this formula that the plane plus the wind equals the resultant. Now, obviously that can be adapted because it's not just planes. Sometimes we'll have some with like currents, water currents, or it could be, obviously many different things. But this is kind of the number one example of this. So the plane, that means the velocity of the plane on its own. Sometimes they say in still air, or if it was a boat, in still water. The resultant is how fast and what direction the object is actually moving. So the resultant is the actual real life velocity. The plane velocity, that's kind of a more theoretical. If there was no wind at all, how fast and in what direction would the plane be moving based on kind of what the speedometer, I don't know if planes have a speedometer, but that kind of thing, based on how fast the plane would be moving itself. The resultant is what actually happens to the plane when the wind is factored in. This is also sometimes called the ground velocity. Because in the plane, the person flying the plane might be saying, oh, look, I'm steering the plane straight north. But if there's wind coming from the east, you're actually kind of getting pushed off to the west. So the person in the plane thinks I'm aiming straight north. My velocity is north because that's the way they're steering. But if there's a wind coming from the east and pushing it a little bit that way, this is the velocity, this northwest direction. That's what people on the ground see. The plane's actually flying a little bit off course. So that's what the people on the ground would see. So this is kind of the velocity from the perspective of somebody flying the plane. Which way are they pointing the plane? How fast are they setting the plane's speed to? When you add in the wind, you get the actual how fast and what direction is the object actually moving. So this is the first example, and it is really the same kind of case with the airplanes. The airplane heads northwest at 500 kilometers an hour and encounters a wind of 120 kilometers an hour. That's a pretty big wind. Careful with the wording here. It says from north 65 degrees east. So we want to determine the resultant ground velocity. And there's kind of a lot of things to think about here. We always have to draw a diagram. So I'm going to draw and label kind of a compass situation here. Now, the first thing was that the airplane is heading northwest at 500 kilometers per hour. So I'm going to put a vector going northwest and label that P for plane. So I'll say let P be plane velocity. I'm going to use W for wind and R be resultant. So the next one, the wind is coming from north 65 degrees east. So if we look north and then 65 degrees east here, if the wind is coming from that direction, it's actually going southwest. So instead of labeling it up here, it's coming from that direction. I'm going to start here and label that there. Whoops, should not have done that quite so big, but there's wind. So this is the path of the wind from north 65 degrees east. Now, just a note when we have this northwest, if an angle's not given in your bearing, that means north 45 degrees west. So it's like exactly at the 45 degree angle there. So we need to draw in our resultant. So I'm going to take the plane, I'm going to add in the wind velocity and draw in my resultant. There. So, oftentimes it is really the angles that are kind of the trickiest piece here. There's different ways to look at this, but I need to figure out an angle of these vectors. So if I just kind of sketch in, there's again lots of different ways that you might kind of analyze these angles. I know that that is going to be 45 degrees. And kind of looking back here, this north 65 degrees west, that's 65 down there. So that would leave this piece in here as subtracting that from the from 90. So here, this would be a 25 degree angle in there. So I can say that this whole angle from the wind to the plane is going to be the sum of those two small angles. So I've got a 70-degree angle in there, and then looking with this here and forming a C pattern with my parallel lines of the two wind vectors there, that would be 110 degrees up there. So it is a little bit more work than when we just had mostly things going north, south, east, or west. It does take a little bit of kind of patience and thinking this through and combining together all of your skills with the kind of triangle laws and parallel line rules. So I'm going to just kind of redraw this same triangle using the wind and the resultant and this 110 degrees. Now I know that the wind was 120 and the plane was 500, and I'm going to put the magnitude of the resultant there. So as you see, we've got a cosine law situation. So the magnitude of the resultant squared is 120 squared plus 500 squared minus 2 times 120 times 500 times cos of 110. So again, I don't need to see a lot of work. I need to pull out my calculator though. This is not a do it in your head one. So when I do all of that, make sure that you get a reasonable number. I get 552.67 kilometers per hour. So if you've drawn an even kind of somewhat to scale diagram, you should be getting a pretty reasonable value there for your answer. And that looks pretty good to me. It does look like that magnitude would be bigger than the magnitude of the plane, but it's not unreasonably bigger, so that looks good. Again, I am not done. Always, if you're asked to find a vector, ensure that you are doing the full amount of work that you need to do. I'm not just asked for the magnitude. I wasn't asked for the speed, the resultant speed of the plane. I'm asked for the resultant ground velocity. So if you're asked for a velocity, we need both the magnitude and direction. So kind of going back to here, I'm going to pop theta in here, and this was kind of my origin back on my original diagram. So I'm going to put my theta between, sorry, I have a cat trying to help with math here. I'm going to put theta between the plane velocity and the resultant, because if I find this theta in there, I know that that's 45. I'll be able to get a good angle for my answer there. So then using sine law, we've got sine theta over 120 equals sine of 110 over the resultant, which was my 552.67. Then calculate that out. And I get that the angle there is about 11.77 degrees. So I'm going to need to interpret that. That would be an additional 11.77 degrees. So I would know, for instance, that was 45, and then that had the 11.77, that this would be a total of 56.77 degrees from the north. Okay, so I'll write my therefore. The resultant Ground velocity is 552.67 kilometers per hour. And remember, we use the square brackets for our direction. I'm going to say north, and then adding the 45 to this is 56.7 degrees, 56.77 degrees west. So make sure, again, it will not specify magnitude and direction. If you just find the magnitude, you've only done half the question. So that's really important to remember.